All right. Sorry about my voice. I just got over a cold. So we're continuing on, and we are looking into one-to-one functions and their inverses. And this is section 2.8. So one-to-one functions. A function f is one-to-one if there is a one-to-one correspondence between the inputs and the outputs. So what do we mean by that? For example, if I look at the function f of x equals x squared, and let's look at some inputs. Let's say when x is -2, the output will be 4. If x is -1, the output will be 1. If x is 0, the input is 0, the output will be 0. If x is 1, the output will be 1 as well, 1 squared, so the output is going to go to this one, and so on. So these are the outputs. So if we look at this function, is there a one-to-one correspondence between the inputs and the outputs? We notice that that's not the case because these two inputs have the same output. So this is a 2-to-1 correspondence. So we would say that this is not one-to-one. However, let's look at f of x equals x cubed, the inputs and outputs. So if I look at a -1, for example, -1 cubed is -1, 0, 0 cubed is 0, 1, 1 cubed is 1, and so on. So notice that for this one, there is a one-to-one correspondence between the inputs and the outputs. So this is, yes, it is one-to-one. So f is one-to-one if it never takes on the same value twice, or we can think about it like if the inputs are different, then their corresponding outputs must be different as well. So if I have two different inputs, let's say x1, which is not equal to x2, so they're different, then their outputs, f of x1 and f of x2, they also must be different. So the reason we're interested in this is because a one-to-one function, so for example this one, is going to give us a way to start from the outputs and get back to the input. If it's not one-to-one, I can't start from the output. Think about it, if I start from 1, I can't get back to the input because I have two inputs, so which one would I get back to? So one-to-one functions are going to be the key to finding another type of function which is called an inverse function. And an inverse function is going to do the exact opposite of what f does. So if x6 inputs does something and gives outputs, the inverse is going to take as inputs the output of f, do the opposite of what f did, and then give as output the input. We'll see in a little bit. Okay, so how to determine if a function is one-to-one? Algebraically, so if you're given the formula for your function, how to determine if the function is one-to-one, we're gonna see if I have f of x1 equals f of x2. So see if this situation, so two equal outputs, what has to be true if the outputs are the same? They must have came from the same input. So see if f of x1 equals f of x2 implies that x1 equals x2. So what we're saying in here is like if I have two outputs, two equal outputs, their input must be the same. Or else, if it's not the case, then it's not a one-to-one function. So let's see. So f of x1 equals f of x2. Well, f of x is 1 over x minus 2. So f of x1 equals f of x2 will mean 1 over x1 minus 2. This is f of x1. Instead of x, I put x1 equals f of x2, 1 over x2 minus 2. So basically, if I work this around, if I get to the conclusion that x1 equals x2, then the function is 1-to-1. So let's cross multiply in here. So then I'll have 1 times x2 minus 2 equals 1 times x1 minus 2. And then if I add 2 to both sides, I'll get that x2 equals x1. So yes, if I start with their images, with f of x1 equals f of x2, and I work it around and I get to the conclusion that x1 must be equal to x2, then yes, f is 1-to-1. Okay, what about for g? So see if g of x1 equals g of x2 implies that x1 must be equal to x2. So let's see, g of x1 is going to be square root of 2x1 plus 3 minus 1 equals g of x2. So square root of 2x2 excuse me, minus 1. So if I add 1 to both sides, this goes away. And then if I square both sides, then I'll get 2x1 plus 3 equals 2x2 plus 3. If I subtract 3 from both sides and divide by 2 both sides, I get that x1 equals x2. So yes, g is also 1-to-1. So algebraically, this is how we determine if a function is 1-to-1. You let two outputs equal to each other and see if solving that implies that the inputs have to be equal. All right. What about graphically? How do we decide if a function is 1-to-1 graphically? Well, if I have a function, let's call this f. Graphically, how do I decide if it's 1-to-1? We're gonna do what we call the horizontal line test. So horizontal line test. This test says that a function f is 1-to-1. Is 1-to-1. If and only if no horizontal line intersects its graph more than once. And what does that mean? So keep in mind that the vertical line test was just to determine if a relationship represents a function. We're dealing with the function already, and now if we're doing a horizontal line test to a function, that is used to determine if it's 1-to-1 or not. So let's see. If I have this function and if I draw a horizontal line test, well, it only intersects it once. What does that mean? That means that for an input x1, I have f of x1. I only have one output. If I draw another horizontal line anywhere, what does that mean? For another input x2, I have exactly one output x. So drawing a horizontal line test means we're making sure that there is a 1-to-1 correspondence between the input and the output. So yes, for this, yes, 1-to-1. What about this one? Well, let's call this one G. Let's draw a horizontal line. Okay, one input x1 has an output G of x1. But notice if I draw a horizontal line here, what is happening there? I see that it intersects it in 3 different spots. That means there are 3 inputs. Let's call it x2, x3, and x4 that share the same output. So this is a 3-to-1 correspondence. So G is not 1-to-1. So this is how you determine graphically if a function is 1-to-1. You perform the horizontal line test. Note, what can we say about a function that is increasing or decreasing everywhere on its domain? So let's see if I have a function that is increasing everywhere on its domain. So from left to right, it's increasing. Well, if it passes the horizontal line test, right? Anywhere I draw a horizontal line, it only crosses in 1. That's the reason if it's increasing everywhere, that means it's not going to come down and decrease and then running the chance of, well, not running the chance, but cause a horizontal line to intersect it in 2 spots. So if you're increasing everywhere on your domain, you're always going to be 1-to-1. Similarly, if you're decreasing, so if you have a function like this, decreasing everywhere, it's also 1-to-1. Any horizontal line test is going to cross it in just 1 spot. Again, because it's not going to start increasing somewhere. All right, so let's practice. If I have a function f of x equals x plus 2 squared minus 1, so let's graph this using transformations. So x plus 2, this is the function x squared. That's the parent function, and it's left 2 units and then down 1 unit. So the x squared will be just your regular parabola going through the origin like that. We're going to move it left 2 units. So the vertex is going to be here now, and then down 1 unit. So this is where the vertex is going to be. So to the left 2 units and down 1 unit. This is x squared plus x plus 2 squared minus 1. Okay, so is this function 1-to-1 on its entire domain? Well, if I look on its entire domain, if I draw a horizontal line test, horizontal line, I see that it crosses in 2 different spots. So no, not 1-to-1. On its entire domain. But is it 1-to-1 on part of the domain? What if I restrict the domain? That's what we say. So what if I just look in here? If I just look at half of this, is this 1-to-1? Yes. What if I just look at this half? It is 1-to-1? Yes. So if I restrict the domain, so what would I have to restrict it to? So if I just look from -infinity to -2, the function is 1-to-1. Or if I look from -2 to infinity, the function is also 1-to-1. So sometimes if we restrict the domain of a function f that is not 1-to-1, it becomes 1-to-1. So f of x equals x plus 2 squared minus 1 is 1-to-1 on -infinity to -2 or on -2 to infinity. So you'll see this is going to become important. All right. So why are we interested in 1-to-1 functions? Well, because one-to-one functions are going to have inverse functions, and inverse functions are important because they're going to be a way to undo what f does. So let's see what we mean by that. So a one-to-one function with domain A, so if I have domain A, I have a function, and range B, so let's say this is f. So f takes an element in the domain A, applies the rule, and then gives you an element as output in the range. So the inverse is going to take on as domain the range of f. So the inverse function is going to leave from here. It's going to take on as input the range of f, and is going to give you as output the domain of f. And we denote the inverse with f to the negative 1. F to the negative 1 does not mean 1 over f. So note, f to the negative 1 of x does not mean 1 over f of x, does not mean the reciprocal. So the inverse, we denote it as f inverse, takes as input the output of f and gives as output the input of f. So if I have an element x in the domain, f of x equals y, then the inverse is going to take the element y, so f inverse of y is going to give you x. So for example, if I have that f is the function that takes the input x and multiplies it by 5, and then adds 2 to it, and then takes the 5th power of the result, what would the inverse have to do to undo what f did? Okay, so let's see what we mean. So f of x, what is f of x doing? Takes the input x, multiplies it by 5. So I have 5 times x, adds 2, plus 2, and then takes the 5th power of the result. So I'm raising it to the 5th power. So this is what f does. Now what would the inverse have to do? Well, the inverse is going to do exactly what f did, but in reverse order and exactly the opposite. So I will start with the inverse, f inverse of x is going to take x, and so instead of taking the 5th power of the result, it's going to do the 5th root of it. So the opposite. So the opposite of 5th power is 5th root. So it's going to do 5th root of x, and then adds 2, so it's going to do the opposite, so it's going to subtract 2, and then multiplies it by 5 was f, so f inverse has to divide it by 5, so it's going to divide it by 5. So this is the inverse. The inverse undoes what f does. So the inverse is going to do exactly the opposite in reverse order. So the inverse property says that if I compose, so this goes back to composition of functions, if I compose the inverse with the function, with its function, I should get x out. What does that mean? It means that f inverse and f, they undo each other. Whatever f did, the inverse undid it. Or the other way, if I compose f with f inverse, whatever the inverse did, f undid it, what f inverse did. Okay, so let's see. I have f of x equals g of 8 minus 4x and g of x equals 8 minus x over 4 are f and g inverses of each other. So for them to be inverses of each other, they have to undo what the other does. So I must have that f composed with g of x is x. So if I have the input x and I apply the g function and then I apply the f function, then I have to end up with x where I started, because the f and g, it's like they cancel each other. So this is what we're asked. But it has to also work the other way. G composed with x, with f of x, has to be x as well. So let's see what is f composed with g of x. So f composed with g of x equals f of g of x. And this is f of g of x is 8 minus x over 4. So now in f, anywhere I see x, I'm going to put this whole thing. So in f, I'm going to have 8 minus 4. Instead of x, I'm going to put this whole thing. Times 8 minus x over 4. 4 cancels, then I have 8 minus 8 cancels. And then negative x is x. So yes, f composed with g of x equals x. Now let's do it the other way. G composed with f of x. This is g of f of x. So let's see if these undo each other. So it's going to be g of, well, f of x is 8 minus 4x. Now in g function, anywhere I see x, I'm going to put 8 minus 4x. So in g, so 8 minus, instead of x, I'm going to put 8 minus 4x. Okay. So this is going to be 8, distributing the negative is going to be minus 8 plus 4x over 4. And what's 4x divided by 4? This is x. So g composed with f of x is also x. There you go. That means that, yes, f and g are inverses of each other. So one important property of inverses and their functions is that the domain of your function f, well, they switch input and output. So the domain of f is going to be equal to the range of the inverse. And the range of f is going to be the domain of the inverse. We'll see how this is going to help us to find ranges.